Thank you for the introduction. And what I want to talk today, I mean, it was a really great session actually that we just had, talking about fault leakage and, sort of larger scale basin sort of modeling. And what I want to focus on here is still talk about risk, but actually focus on the sort of near well processes. Some of the things actually my introduction is sort of covered very well already. When we talk about risk assessment for CCS, usually we talk about containment. Of course, there's seismicity as well. In the Netherlands, we look at offshore where seismicity is less of a concern for us. So containment risk assessment, generally we agree, we have spillover points, we have fault leakage, potentially could have caprock integrity issues. And finally, we have well leakage. Now, in most regulations that we have so far, usually the pressure of a system is set according to your caprock or reservoir sort of fracture initiation pressure, some form of that, and then you have a factor of safety added to it. So this is sort of the standard practice. However, when we come to CCS, I mean, the pressure budget, we need to kind of, we argue that we need to also include the wells. So what are the pressure budgets that you have, considering the legacy wells in the vicinity of your project, also even your injection wells, and there's a certain point that your wells could be the risk. So what would that? We want to develop tools that would essentially help us evaluate that the pressure budget you have just based on your wells. Um, so just the run of the mill sort of an example of a framework for risk assessment. What we want to do is we want to look at um, particular ways or hazards that we have in particular for a CCS project. For the hazard, we can use different types of modeling to understand. At the end of the day, we want to know what is the potential magnitude of an event or a leakage we're going to get, and what is the probability of that. What is different here from seismicity is that I would argue the location of leakage also is quite important, because if you want to do sort of damage modeling or some sort of consequence modeling, whether that leakage is to the surface, whether it's near a populated area, or it's going to be to the seabed, or an overburden, it's going to be a vastly different sort of damage or consequence analysis. So today we really just focus on, I mean, again, this morning we talked a lot about fault leakage. Lateral migration is more of a dynamic reservoir problem. Caprock integrity, I would say, argue again, we talked about it to some extent. So I want to focus particularly on well leakage. Now at TNO, we have been working on that for a few years. We've developed a tool at the moment. It's called CREST. What it does is it builds sort of a near well hydrothermal mechanical model. It mimics sort of a well bore where we model the entire well's history, from the drilling to your cement placement, your curing, hydration, then how you operate the well. And this could be a legacy well or it could be your injection well. And based on the stresses around the well, we sort of understand, okay, can this cement sheet be damaged? I now showed his modeling framework where it shows, okay, is the caprock going to be damaged? So we're doing a similar work here on the cement sheet. So can that cement sheet be damaged? To what extent? And then if we have that, then what sort of leakage rates can we potentially get based on the CO2 pressure plume we have around this well? So we've published this methodology, two recent publications, so I'll let you kind of look at that if you're interested in details. So I'm not going to go through all the math behind this, but that's the general purpose. And what we're doing differently is, generally well leakage is addressed probabilistically. It's really easy to estimate the leak rate because, if you just make up a cement sheet permeability and then say, okay, my entire cement sheet has this permeability and this is my delta P, then sure, it's a very easy back of the envelope calculation. The problem is nobody knows what a cement sheet permeability is. And we argue, and what we want to do is use sort of mechanistic models, physics-based models, to, by coupling geomechanics and well leakage, understand when these defects will actually open. In fact, they're quite dynamic. They're not always open or closed. They do open and close as you operate your well. And then, so you have your pathway, but then at the end of the day, you also still need a pressure gradient to be able to leak out of your system. So the combination of these would give an indication of whether your well is going to leak, how much, over what period of time. Um, so again, just going through some of the physics, like looking at your caprock and how it's going to behave, whether it's going to have plastic flow, what we call creep. Your cement hydration process is quite important because the initial stresses in cement are quite complicated. So there's a lot of kind of physics and a lot of independent projects and studies that have gone into the background for this tool. Um, Another point about well leakage is a very broad term, but and it could actually mean very different things. Um, the leakage pathway is not always very simple, right? So the leakage pathway could make all its way, inside the well and to the surface, or it could be on the outside of the casing, still make its way to the surface, or it could go into various formations along the way. In this particular example, I'm going to show you, I mean, this is from the return project. And this is a simplified approach where we look at, okay, what if CO2, if this is the casing and you have a cement sheet and there is a leakage pathway, if it is open, this is a storage reservoir and CO2 can flow upward and into this overburden, okay? So this is just one of the possibilities, but there could actually be other pathways potentially present. Um, so this tool here, so we kind of started looking at some case studies. It is in our papers. This particular one, we sort of looked at a synthetic well in the North Sea. So it's based on realistic well data. We have a 7-inch liner going through the caprock. It's a shale caprock. We intentionally didn't look at Zechstein. Zechstein is much better. It's quite, especially the areas where it's really thick and you know that it creeps. So this is intentionally picked as a case. Again, we're trying to break things so that to show that our models actually can predict things. In this particular well, the initial reservoir pressure was 274 bar. It is produced down to 50. This is a very typical case in the North Sea. And then we want to inject CO2. One question in the Netherlands, typically, by how much, how far are you going to increase the pressure again? So here, we start with a very conservative case of 240, and then we, take it back up to 174. Theoretically at 274, the initial pressure, should hold in terms of caprock and fault. Of course, there is some hysteresis, so one could argue with plastic movements, there could be some differences. But, overall, this reservoir has experienced 274. Why can't we go back to that? So we want to answer this question particularly just from a well's perspective. So this is the operational condition for this well. Initially we modeled the depletion in the first 10 years, I believe. Then we have very instantaneous sort of CO2 injection. The temperature drops quite drastically, and then so this is the pressure that is declining due to depletion. And then the pressure starts increasing. Temperature gradually increases as well as the pressure increases due to CO2 sort of phase behavior. We also modeled like 1 year sort of post-injection period just to see, if you stop injection, and you allow some pressures and temperatures to equilibrate, what happens to your leakage pathway and so on. So looking at the first leakage pathway. So in this particular case, we have a very overpressured caprock, and we actually anticipate a microannulus or sort of a pathway in the cement opening as the cement is curing due to those initial conditions or stresses in cement. So the cement density here is particularly, and the length of it is not high enough. However, as you start producing this reservoir down, you actually close that gap. So again, this is the dynamic part of the leakage pathways. They're not always open or they're not just the same size. They actually evolve over time. So this is a case where there's no caprock creep, and this is a case, the blue one, the caprock actually creeps. So then you start, so the pathway is closed, you start injecting CO2, gradually you start opening that up again because the stresses will be in that way. Of course, as the caprock has that plastic capabilities, is creeping, then it takes quite a lot longer for you to open it, and finally the size will be a lot smaller. So kind of characterizing your creep, the creep for the caprock would actually change the using per se lab experiments, for example, it can change the risk assessment quite a bit, or the results of the risk assessment quite a bit. And then you start injecting CO2, and then eventually you stop, and then because of the temperature changes, the size of the pathway will drop again. And this is the lower one is the case where we have a higher versus lower pressure. So if you inflate the system, essentially, you're inflating the leakage pathway as well. That's really what it comes down to. Okay, so we have a leakage pathway. It's dynamic. It could, be present at some points. What happens to the leakage rates? So the base case, if we assume that we don't go over 240 bar, we don't anticipate any leakage. This has been, cause of debate at some point. It feels a little counterintuitive. It's a gas, it should kind of move upward no matter what. But again, remember that there's an overburden at a much higher pressure than the CO2, where in fact the direction of flow on the outside of the casing, so here we're talking outside the casing, not inside, there's pressure support from this overburden. And there's the CO2, even considering buoyancy, this includes buoyancy, does not have enough of a pressure drive to move upwards through this gap that is, 100, 200 micron. Okay. So there is a theoretical pressure, depending on the depth of this overburden, permeability, and so on, that you physically are not able to leak out of the system. Okay. Usually, and that is set a little bit case by case, but you can assume hydrostatic if you really want to back out the envelope calculation. That should be your limit. It's probably a little bit lower than that because of the buoyancy and so on. And then, okay, so that's the conservative limit. Then we start, and again, this doesn't include inside the well, because inside the well doesn't have the same pressure support from formations, right? So if you have a legacy well with no cement plugs, you can leak from at any pressure with gas. Okay, so buoyancy does exist. That's not what I'm saying. Okay, so we start injecting at a pressure a bit higher. So then at a certain threshold, you start leaking on the outside of the casing and into the overburden. Thankfully, CO2 at these pressures, this is 2,500 meters depth. It's still fairly heavy, so the buoyancy is not going to be so significant. And then depending on what physics you consider, so if you look at the non-Darcy effects and you look at the creep and so on, you're going to get a range at least of what sort of magnitudes you're going to get for leakage. This would be a bit better plot. So again, I think of this as, you have a little needle in your reservoir. Eventually, if you increase the pressure, you're eventually going to pop that, right? So it's a matter of what is that limit. And then the higher your pressure is going to be, the more the gas is going to kind of, flow out of this zone. And what we're seeing here is, again, there is a particular threshold that probably your leakage risk is very low. Beyond that, you start increasing that to some extent. And by how much, I think, is the more important question. The base case here really assumes everything is, a single phase flow. It's very, very, very conservative assumptions. When we look at a little bit more meaningful physics that are very easily observable in the lab, then you get around, let's say, 300-400 tons a year. And again, this is, for example, you're looking at 10 megatons, so 10 million versus 400 tons of leakage. So the order of magnitude is quite low compared to how much we're injecting. So the purpose here is for us to say, okay, we need these sort of tools to understand what the order of magnitude, because without it, leakage sounds really scary. And also, at the end of the day, we need to decide. I mean, at what level of risk is acceptable to us. So the thing is, the final storage pressure. I mean, if you increase that to 274, you're adding quite significantly to your storage capacity, right? So in this example, I mean, 34 bar increase means 14% increase in your capacity, means you're going to store a lot more CO2. And this is beneficial not only from a climate standpoint, but also quite economically improves the projects quite significantly. At the same time, then you have some sort of a consequence, a damage analysis needs to be done. Okay, what happens if there's 1,000 tons of CO2 in the overburden? Is that just going to dissolve in the overburden and stop, assuming that at abandonment you've stopped everything and you've successfully abandoned the well? So I think this is a I guess what we're the reason we're building these tools is that we need these numbers, we need this quantitative assessment to be able to do this kind of analysis. And at the end of the day, I mean, there was a comment on how are we finally going to make decisions, and how are the governments going to, you know, give us the permission to start injecting. I mean, at the end of the day, we need to say, okay, well, these are the potential consequences. If it's not acceptable to you, either we have to abandon the project or add new mitigation measures, or the project will be 10 times more expensive. Like there is, at the end of the day, will come down to these numbers. I think for the most part, we're there. It's just taking, I think, a little bit just slower. Uh, but that's all I have for today. Thank you so much.